Hi everyone, and I'm a PhD student from AWI. And today I'm very excited to talk about this topic and hope you could give me some suggestions on this. And during my PhD, I was doing the work that related to high resolution simulations, and I'm quite interested in the Arctic Ocean eddies. And firstly, I'll give you some motivation of my work. And I guess in this room, you have already known a lot about the mesoscale eddies. The mesoscale ocean eddies are characterized by small-scale swirling motion. This picture shows the satellite data sets records, and in most of the eddy-rich regions, the eddy kinetic energy has to increase so much in the past time. And also, if you look at the originally eddy-rich simulation from Nathan Beach last year, and in most of these eddy-rich regions, we also have the increase of the eddy kinetic energy. But actually, in the Arctic Ocean, we now have less understanding of it, why this happened. And one reason is that we have a sparse observational data set, and the other is, and if you look at this figure, it shows the number of the Rossby radius, and it is actually 1 to 15 kilometers, which is much higher than the SIMIP6 models, so that most of the state-of-art hydrodynamic models are not really eddy resolving. So here comes to my research question is, if I use a eddy resolved model, what results can we get in the Arctic Ocean? And I will give you more motivation of my work is the rapid change of the Arctic Ocean. And we have a relatively rapid warming Arctic and compared with the global ocean. And based on the recent results, and it is almost 4 times faster than the global ocean. And we also have relatively a large decrease of the Arctic sea ice, so that the Arctic Ocean is changing really faster than we expected. So what will happen to the ocean eddies based on this background? And here comes to my research question is if I use the high resolution model, what will happen to the Arctic Ocean eddies from past to the future? So here is my model setup. And I used the FASM2 model from our institute, and it is an unstructured model. And I now have 143 years eddy permitting simulation, and we have 4.5 kilometers inside the Arctic Ocean and around 30 kilometers outside. And we also have 3 time periods from 2010, 2050, and 2090. And we actually took the initial condition from the 4.5 kilometer simulation. And it is not really a cold start, but from features that we think is decent. And forcing data is taken from the RVCM. And for the future scenario, we are using the SSP 585, and it gives us a 4K warming world. So now I'm going to show you some results. So from this figure, actually, Thomas showed you yesterday, and described a little bit. And on the left is the surface velocity field, and in the middle is the 50-meter velocity field, and on the right is the CS change. And you can see in the future, yeah, and we have relatively an ice-free Arctic Ocean, but in the past time, we have compact and immobile sea ice covered at the ocean surface, and consequently, we have a relatively less eddy activity in the past time, but we have a really eddy abundant future period. But if you look at the 50 meters, and we even have some coherent eddies in the past time when we have compact sea ice cover, because it's not at the surface, only at the surface ocean when there is sea ice cover, and eddies will dump quite a lot. But in the future, we have abundant ocean eddies. So here is the eddy kinetic energy and sea ice in a seasonal time scale. You can see that this actually anti-correlated. And in the long term, it also shows that the sea ice will dissipate eddies quite a lot at the ocean surface. And to be more statistic, and here is the figure shows in a 4K warming world, with the declining of sea ice, we have an intensify of the eddy kinetic energy in the Arctic Ocean, which is defined here in the Arctic Ocean, Eurasian Basin, Canada Basin. And it is almost 3 to 4 times higher than the past time compared with the future. And in the 1 kilometer simulation, which is these short lines, and they have relatively higher increase compared with the 4.5 kilometer results. And if we compare with the global ocean, because Nathan also did a research to see what happened outside Arctic, and he find a standard deviation in his paper, which is indicate the historical period, and he gets this number of 4, 5, 6, and even minus 2.5 standard deviation increase in the future compared with the past time. But actually in our Arctic Ocean, we have 15 standard deviation, which is much higher than the global ocean, the other rich regions. And so this indicates that we really have a stronger increase of the eddy kinetic energy in the Arctic Ocean, and we also have a relatively short and smaller value in the past time. So we really want to understand why this happened. So here is some mechanisms that I will show you later. And the first one is the eddy generation, and then I will show you the dissipation term. So here is the baroclinicity, and actually this term is, and the definition is from the conversion from the available potential energy to eddy kinetic energy, and this happened because of the change of stratification. And from this figure on the left is in the past time, you can see that the EKE and baroclinicity, they are really highly correlated, and they are elevated at the Front Strait, Eurasian Basin, and the southern Baltic Sea and Lomonosov Ridge. And if you look into the future time, this yellow with orange label, and they also elevated in these regions, which give us the point that the baroclinicity, the eddy generation tends to generate and maintenance a lot of eddies in the Arctic oceans and make the eddy kinetic energy increase so much. And here comes the eddy cooling. And I heard a lot of you have already discussed this eddy cooling in your presentation, and briefly talk about the definition of it is that because the sea ice and the wind will have the friction on the ocean, so that it will dissipate eddies and also remove the energy from the ocean. And here is the eddy cooling I get from my results. It changes and depends on when I'm using different kilometer bond. And in our simulation, when we look at the energy, the spectrum of the eddy kinetic energy, we will get a peak at the 50 kilometer. So that here I use the 50 kilometer as the definition of the eddy cooling term. And on the right is the corresponding figures. And one thing is really interesting to us is that if you look at this figure, and actually it is in the future, but we have a relatively more negative eddy cooling, which means that the eddy are cooled even more with actually less ice cover. And I think this is a little bit out of our understanding, because if there's less sea ice cover, the eddy should generate quite a lot, but not dissipate quite a lot. So what we're trying to explain here is that in the future, we have more eddy generated, so that even if we have less sea ice cover compared with the past time, we can still dissipate quite a lot of eddies, because we have more eddy generated, so that there's more eddy to be killed. But in the summertime, because here you can find out that it is almost an ice-free Arctic, so that we can't dissipate quite a lot of eddies. So that's the question that you can see here. In the summertime, we have relatively less dissipated compared with the past. So I don't know if I described clearly, but you can ask me later. So to conclude this, we have the eddy-rich Arctic. If I use the eddy-resolve model, activity has increased from 3 to 4 times, and it is mainly reduced by the eddy generation term, but the eddy cooling term will also increase in future because of the change of the eddy generation. So, and if you have some questions, you can just ask me. I just stop here.
You're saying that eddy becoming stronger because of stratification.
Yeah, because the available potential energy just increase, and
yeah, I mean if you say that's because volcanicity is increased, actually you should have stronger vertical shear and actually stronger horizontal shear in your but warming itself, that means warming is more homogeneous in space. So my question is, how do you get to this horizontal shear in temperature? Shear in
Actually, I think, I personally think it is because of the change of salinity, because it's much more.
But you need a spatial gradient in salinity to produce. I mean, how do you get the spatial gradient? That's because of the river? Or?
It is because of many things in sea ice melting and river runoff. Yeah.
Okay. That produces spatial information.
Yeah.
Okay. Sounds good. Yeah.
Do you have a sense of the life cycle of these eddies? Are they mainly staying fairly stationary, or are they moving around?
I didn't show the animation of it, but it is, I mean, stay in not moving so fast based on my animation.
Yeah, thank you. Very interesting. Do you have a sense for to which extent this depends on the sea ice model you use, or how you represent interactions of sea ice and ocean?
The sea ice data is also taken from the RVCM forcing. Yeah, and so is this your question? And any our parameters? And for the CS, we are using relatively lower albedo and compared with our past simulations.
Yeah, I guess my question is to which extent fluxes and momentum transfer penetrate through sea ice or not, and how that would then affect this or not.
I can't understand this question quite well. Maybe we can discuss later.
Yeah, I have.
I think there's another talk.
Yeah, but now it's.
I have just
something
very briefly, as long as you are up there and you have goodies, and it looks a bit strange that I from RV give a goodie to someone else from RV. So what we did, what?
It's not RV. We are smart.
No.
Goodies are not.
Yeah, so okay, sorry. So up front, as we said, we decided we give a few goodies away for good reasons. And Xinyue was the only one actually meeting the deadline and giving us the presentation, okay?